The center of mass variables are called translational variables or translations. Then, depending on whether the molecule is linear or non-linear, 2 or 3 variables are chosen to describe rotational motion. Two variables for linear molecules. These are the theta and phi variables that we have used before to describe the motion of a diatomic molecule. Remember, a diatomic molecule is a special type of linear molecule. For example, as a normal geometry of acetylene molecule, acetylene contains how many atoms? C2H2. There are 4 atoms, and the normal structure is linear. All the carbons and hydrogens are on the same line. To describe the rotational motion of acetylene molecule, we just need 2 variables, just like any diatomic molecule. On the other hand, if the molecule is nonlinear, then we need 1 more variable to describe the rotational motion. 3 variables for non-linear molecules. The variables taken are same as here, theta, phi. 1 more angle variable is needed, and the usual symbol, the standard symbol for it is chi. So 3. All of these are angle variables. So these are rotational. The remaining variables are called, by definition, vibrational variables. The total number of variables is known from the outset. What is it? 3 times m. 3 variables are taken as translational variables, 2 or 3 taken as rotational variables. The remaining variables is vibrational variables. Vibrational variables are 3 times m minus 3 minus 2 if the molecule is linear. 3 plus 2 is 5. So this is for linear molecules. On the other hand, it is 3 times m minus 6. 3 plus 3. We are subtracting. The remaining number of variables is 3 times m minus 6 for non-linear molecules. Number of vibrational variables also gives us number of vibrational frequencies in the molecule. So we may say this: a linear molecule has 3 times m minus 5 vibrational frequencies or vibrations. On the other hand, a nonlinear molecule has 3 times m minus 6 vibrations. There is a difference, slight difference between the term vibration and vibrational frequency. Vibration is physical motion, all right? So a linear molecule, for example, will have 3 times m minus 5 different vibrational motions. On the other hand, frequency is a number. When we say 3 times m minus 5 frequencies, some of these frequencies may be identical to each other. In other words, it doesn't mean that there are 3 times m minus 5 different vibrational frequencies. But as far as the physical motion is concerned, there are exactly 3 times m minus 5 physical vibrational motions. Some of these physical vibrational motions may have the same vibrational frequency. For example, if you take a linear, say, okay, A, B, C, linear structure. There are 3 atoms. So for the linear structure, 3 times 3 minus 5. 3 times 3 is 9 minus 5. There are 4 vibrational motions. And there are also 4 vibrational frequencies. However, well, let us show what the vibrations are. Now, assume this bond is stretching outward, and this one is also stretching outward. Then if B is different from A and C, one possible vibration could be like this. Another one if A and B are stretching, then the third atom could go in the opposite direction. So these are different types of vibrational motion. There are so far 2. There should be 4. The third one could be the terminal atoms. If they are moving upward, then the center atom must move downward. Here, when I select the directions of the arrows, just keep in mind that by definition, during the vibrational motion, the center of mass of the molecule must stay fixed. All right? So, not if I attach arrows, all of them upward, that means I'm moving the molecule upward, but that is together with the center of mass. However, center of mass must be fixed. During the vibration motion, center of mass does not move. The fourth vibration is if you take this picture here and rotate 90 degrees. That's a different motion, because the directions are different. However, in other words, if I write it, show it A, B, C, say when you rotate this picture by 90 degrees, Okay, this will go in the opposite direction. Now, the frequency of this vibration is expected to be different from the frequency of that vibration. And these two frequencies should be different than the vibration, the frequency of this type of vibration. But if you compare these two vibrational motions, what do you expect for their frequencies? They must be exactly the same, because the only difference is that one picture has been rotated by 90 degrees to get the other vibration. Physical motions are different here, but the frequencies are same. So, in a linear molecule, when you count the total number of vibrations, number is 4. 1, 2, 3, 4. But numerical values for the vibrational frequencies, if we ask how many different vibrational frequencies do we expect, we expect only 3 different values for the frequencies, because these two vibrations have the same frequencies. This partitioning of the 3 times m variables into a center of mass variables or translational variables, rotational variables, and the remaining as vibrational variables is very useful, and please keep that in mind, because you are going to see this 3m-5 or 3m-6 in other places in your physical chemistry or inorganic chemistry courses. Rule is very simple, and you see how it arises. Okay, now in this factor, translational factor times rotational factor times vibrational factor, this function depends only on the translational variables, these 3 variables. The second one, rotational factor, depends only on the rotational variables. If it is a linear molecule, there are just 2 angles, and if it is nonlinear, there are 3 angles. And the third factor depends on the remaining variables, the vibrational variables, and that's why we call it the vibrational wave function. This is the Hamiltonian for the nuclear motion, Hn. And the total Hamiltonian for the nuclear motion only is approximately translation Hamiltonian plus rotation Hamiltonian plus vibration Hamiltonian. This is approximate. Separation of the translation from the rest is exact. Translation motion can always be separated exactly from the full Hamiltonian. However, separation between separating rotational motion from the vibrational motion is not exact. In other words, there is a coupling between rotational motion and vibrational motion. However, the effect of coupling between vibration and rotational motion is relatively small. So in a first approximation, we treat them as separable. This means that each of these 3 factors are independently obtainable. So translational part in this factor is obtained by solving the translational Schrödinger equation. What you see here is just particle in a box problem. In this case, particle in a three-dimensional box problem. So we have already solved it. This factor psi rotation is obtained by solving the rotational Schrödinger equation. We have studied this equation also before when we discussed the rotation of a diatomic molecule around its center of mass. So this is also known. And then the vibration part is obtained by solving the vibrational Schrödinger equation. And we have given or studied an example of vibrational Schrödinger equation in the case of diatomic molecule. So this is also solved like that. Then we come here. We see that our final result is, let me put it this way, psi, the total state function is a product of electronic state function. This is the electronic state function times a translational function times a rotational function times a vibrational function. This energy, the nuclear energy, is sum of translation plus rotation plus vibration in this approximation. And the total energy is just total nuclear energy plus the electronic energy. So our final result, translational energy plus rotation energy plus vibration energy plus electronic energy. This is, what you see here is the final result of the Born-Oppenheimer approximation. Our original problem is extremely complicated. Please be aware of it. There are 3 times n electrons, and also there are 3 times m atoms, nuclei. They're all moving. And we want to find out what is the total energy, which values are allowed for the total energy. This procedure, this approximation, is telling us that we may proceed step by step. In the first step, we determine the electronic state function together with this electronic energy as a function of the molecular geometry. That's the first step. We must proceed in stepwise. First you do this, then do other things. The first thing we do is we solve the electronic Schrödinger equation to determine this electronic state function and also the corresponding electronic potential energy surface. After we obtain the potential energy surface, we use it here in the second step to solve for the motion of the nuclei. In fact, that energy, that U term or electronic energy, is used only in this, for this part, for the vibrational part. Because translational motion and rotational motion have no potential energy. They are just kinetic energies. But it is the vibrational part in which the potential energy surface is used. This way, by independently solving a translational Schrödinger equation and a rotational Schrödinger equation, then a vibrational Schrödinger equation, we obtain allowed values for translation energies, rotation energies, and vibration energies. And then to get the total energy, we have a very nice sum. The total energy of a molecule is the sum of translation energy of the nuclei plus rotation energy of the nuclei or molecule plus vibration energy of the molecule plus electronic energy of the molecule. And the total state function is a product like this. In most applications, the translation energies do not change when the state changes. And therefore, in spectroscopy, for example, when light absorption or light emission from the molecule, what is important is the rotational, vibration, and electronic part, because the translational state doesn't change when light is absorbed. If the molecule is going overall, like, because translation means that, overall motion, the molecule continues in the same translational state when light is absorbed by the molecule. The rotational state or vibrational state or electronic state may change. Now, let us look at this expression and determine what is the smallest possible value for this total. The smallest possible value is going to give us the absolute ground state energy. To find that, we need lowest value for each one of these contributions. Lowest value for, let us start with, okay, translation energy. Here, this equation for the translational energies is the particle in a box problem. However, in this discussion, the particle is the box size is large. It's a macroscopic box size because we are thinking about a test tube filled with molecules. That's a macroscopic, large size. Now, if you remember the energy formula for the allowed energies for a single particle moving in a one-dimensional box, it was h squared over 8 times m times a squared, where a is the size of the one-dimensional box. If this a is a macroscopic number, if a is a large number, like 1 centimeter even is a large number, then the value of this quantity is extremely small. In that case, the translation energies are continuous, almost continuous, because the energy spacing between one level and the next one depends on this expression. And if this A is a large number, if it's a macroscopic number, then this is nearly zero for large A. So, The smallest value for the translation energy is, as in classical theory, it is 0, the smallest value. For the rotational motion, you should remember it from rotation of a diatomic molecule. Both quantum mechanically and also classically, the smallest value for the rotation energy is also 0. 0 rotation energy means the molecule is simply not rotating. It is 0. So lowest value for translation energy is 0. For the rotation energy, it is also 0. The lowest value for the vibration energy, however, is not 0. Remember, for a diatomic molecule, the expression for vibration energy, allowed values of vibration energy was a constant, energy constant, times V plus 1/2, where V takes values 0, 1, 2, and the lowest value according to this expression is 1/2 F0, lowest value of vibration energy. This is for a diatomic molecule, but a diatomic molecule has how many vibrations? A diatomic molecule is a special case of linear. What is the general expression? 3 times m minus 5 for a linear molecule. For a diatomic molecule, m is 2. 3 times 2 is 6. Subtract 5, you get 1. There is just one vibration. And as you know, it is this vibration, this type of, because center of mass must be fixed during the vibration. There is only one vibration, and the vibration, the lowest vibration energy is this quantity, 1/2 F0. This quantity F0 was h times vibrational frequency, or h times 1/2 pi times square root of force constant divided by reduced mass of the diatomic. This expression is valid only for a diatomic molecule. For polyatomic molecules, whether linear or nonlinear, there are more than one vibrations. And as we said, if the molecule is linear, we have 3m minus 5 vibrations. And if it is nonlinear, there are 3 times m minus 6 vibrations. The general expression for polyatomic molecules for the vibration energy is, now we have more than one vibration. So we have h times nu j times vj plus 1/2, and this is the sum over j from 1 to 3m minus 6 or 3m minus 5, depending on whether the molecule is linear or nonlinear. Okay, the lowest value here, each Vj take 0, 1, 2, and notice we have labeled different vibrational frequencies with the subscript J. So, for example, if we have water molecule, how many atoms are there? 3 atoms. This is the normal structure of water molecule. It is bent. It is not linear. So this is a polyatomic molecule, non-linear polyatomic molecule. Number of vibrations here is how many? 3 times m minus 6. M is 3 here. 3 times 3 is 9 minus 6. There are 3 vibrations. We are labeling these vibrations with the symbol nu1, nu2, and nu3. These are the 3 different vibrational frequencies for the water molecule. If we apply it to this expression, J ranges from 1 to 3. 3 different frequencies. And each vibration motion has its own set of vibrational quantum numbers. So V1, V2, V3 in the case of water molecule, each one will take values 0, 1, 2 independently. So the lowest value for the vibration energy is when you select vibration quantum number as 0 for all vibrations. In that case, we will have simply 1/2 this expression for the lowest. Now, this value is relative to the minimum of the potential energy curve. So the potential energy curve was like this. Okay. This was the electronic energy, fixed value. This is R0. And you see it from here. The lowest value for total energies, lowest value for this quantity, translation energy, is 0. This is 0. This is this expression above the electronic energy. In other words, it's a value up there, higher than this electronic energy. So let us indicate it by a dash inside this curve. This energy, relative to the minimum of the electronic energy surface, is exactly what we called the 0-point energy, 0-point vibration energy. So this quantity is 0-point vibrational energy, and the difference here this is 0-point vibration energy. What you see by this yellow line is the lowest possible total energy of the molecule. What is important is that the lowest energy is not the minimum of this potential energy surface. It would be only the electronic energy. But it's a number which is higher than the electronic energy. So the lowest value is lowest value by definition is the ground state energy, is electronic energy plus 0-point vibrational energy, numerically. Now, we may compare the concept of dissociation energy. This energy difference here, we had previously called dE. The energy difference between the minimum of the potential energy surface and this asymptotic dissociation limit. Now you should understand a little bit better why we called it electronic dissociation energy, because this curve is electronic energy surface. All right? The experimental dissociation energy is the energy needed to dissociate the molecule, AB for a diatomic, into A plus B. Minimum energy needed to cause this process. The right side is dissociated atoms, and according to this figure, this is, here are A plus B. Here, this is, molecule is bound, AB. The total energy of this minus the total energy of AB is, by definition, dissociation energy. Now, the total energy of A plus B is this value here. But the total energy of the bound molecule is not the electronic energy, but it is electronic energy plus the 0-point vibrational energy. Therefore, the true dissociation energy is this difference. And it is called D0. D0, therefore, corresponds to the experimental dissociation energy. And of course, the relation between them, you can see from the graph. dE is D0 plus 0-point vibrational energy. Theoretically, we calculate the electronic dissociation energy, because in the first step of the Born-Oppenheimer approximation, we must obtain the potential energy surface. It is this curve. After obtaining the curve, we know what this value is, which means we also know from the calculation what is the total energy of A plus B for large R. Therefore, we can determine the dissociation energy simply by subtracting this number minus the lower value. Then, using this curve, we go to the second step of the Born-Oppenheimer approximation, and we solve for the vibrational Schrödinger equation and obtain the vibrational frequencies. That way, we obtain 0-point vibration energy theoretically. This is known, then dE minus 0-point vibration energy will give us D0. D0, then we compare it with the experimental value, all right? Because we have available experimental dissociation energies, and we see if they match. And such calculations are not done by hand. They are, both the vibrational part and the especially electronic Schrödinger equation is complicated. However, there are computer programs available. So all you have to do is just input the molecular geometry, and then the program just calculates it for you. And you may obtain very satisfactory numbers, and many people are working with such programs. Even people with no knowledge about quantum chemistry. That's interesting. For example, we have several organic chemists in our department, say Metin Balcı, Metin Zora. They are doing such quantum calculations, but they have very little idea about quantum chemistry, because everything is quite easy, friendly, the computer programs. Graphical interface is very nice, and it is, when you input data, it looks like you are drawing the molecule. Actually, geometry of the molecule is being input to the computer program, but you don't have to think too much about it. Nevertheless, together with the computer programs, calculation of all of these things is quite systematic, and reliable results can be obtained. Before we stop, let us look at some exercises. In one exercise, find the number of vibrational frequencies in the following molecules. One of them is benzene molecule. Benzene has 6 carbons and 6 hydrogens. Is it a linear or non-linear molecule? Non-linear. So, number of vibrations in benzene will be 3 times number of atoms minus 6. Here M is 6 plus 6. There are 12 atoms. Number of vibrations is 3 times 12 minus 6, or 30 vibrations in benzene molecule. Benzene molecule is a symmetric molecule, as you know. Therefore, not all 30 vibrations will have different frequencies. Some of them may repeat. Physically, there are 30 vibrations. But if you ask how many different vibration frequencies are there, then number of different vibration frequencies will be smaller than 30, because some of the vibrations may have the same frequencies because of symmetry. Another one is ammonia. Ammonia is also nonlinear, isn't it? So here M is 4. 3 times 4 is 12, minus 6 is 6 vibrations. Again, in ammonia, the normal structure of ammonia is also symmetric. So, number of different vibration frequencies will be smaller than 6. Another one is acetylene. Now this molecule is a linear molecule. M is 4. Number of vibrations will be 3 times 4, 12, minus 5, or 7 vibrations are present in this molecule. Now, please note that in the calculation of 0-point vibration energy, you must add up exactly the frequencies of 30 vibrations, for example, in benzene. You are not going to select only different ones, but if there are same values for different vibrations, you should add all of them. One last example is water. In water, M is 3. There are 3 vibrations. And the vibrational frequencies are in wave number 3657. Another one is 1595. A third one 3756. These are in wave number units. The experimental values for the vibration frequency in water. There are 3 of them. You see all of these are different. So number of different frequencies, vibration frequencies, is the same as number of vibrations here. It simply means each vibration has a different frequency. In fact, the actual motions are like this. This is stretch. You see, I have moved oxygen in the opposite direction. Why? Because in a vibrational motion, center of mass must stay the same. This is a stretch. This one is expected to have the largest frequency. What is it? It is this one. This is another vibration. Here, how can you describe such a vibration? Bending. Now, you may easily conclude about the vibrational frequency. Is it this number or that number? To answer this question, just ask, which one is easier, bending motion or stretch? Bending is easier. Easier means less energy, smaller frequency. So this corresponds to the bending vibration motion. This is also related with stretch, but this is called symmetric stretch. There is another type. It is called asymmetric stretch. It is like this. If one of them is moving like that, this is moving in the opposite way. Now, to keep the center of mass fixed, the oxygen should move now this is moving. It should move this way a little bit, because the arrows indicate motion to the left, so to keep the center of mass fixed. So such a vibration is called asymmetric vibration, and it corresponds to a large value. You see, symmetric and asymmetric stretches have large frequencies, large values for frequencies, and they are expected because stretching is more difficult than bending.